Hello and welcome to Bay College's video lectures for 095. This is the continuation of section 7.1. We're just going to review the rules of exponents that we introduced, and then we're going to explore scientific notation. And we really have to have a mastery of our rules of exponents in order to work with scientific notation. So to review, recall our product rule for exponents is if we have a product, we would add them if they have the same base. So here we just add their exponents because their bases are the same. The quotient rule, well, since multiplication and division are opposite operations, we're going to do the opposite operation. Here we have quotients, so we're going to subtract the top minus the bottom. The one thing we have to be careful of, it's always the top minus the bottom. For the power rule, if we have a base to a power raised to a power, we have an exponent raised to an exponent, we can simply multiply them. The power of a product or the power of a quotient, this example applies to both. If we have a product or a quotient or a combination of those raised to a power, we distribute the power to each thing within those parentheses. So we just distribute it to each thing. Then we have the zero rule of exponents. Anything to the 0 power is 1, unless that base is 0. If any of these bases are 0, none of this really applies. And then we have the negative exponent. If we have a base to a negative exponent, we can take its reciprocal. Or if we have a negative exponent in the denominator, we can move it to the numerator or take its reciprocal. It's the same rule. All right, so how do these rules apply to scientific notation? Well, scientific notation deals with exponents as a factor of 10, 10 to some power. And this is a very commonly used notation because our number system is based on factors of 10. If we move any value to the right or to the left of a decimal in a number, our decimal system, we're changing by a factor of 10. We have the ones, the tens, the hundredths. We have the tenths, the 1/100ths. We have the 1/1000ths. So we're moving from the decimal a factor of 10. So when we're dealing with really huge numbers or really small numbers, scientific notation can actually simplify our math operations if we know our rules of exponents. So how we write a number in scientific notation is the number times 10 to some power, which basically this number is somewhere equal to 1 or greater, but less than 10. So it could be, as an example, 3 times 10 to the 5th. 3 is somewhere between 1 and 10. So we have a times 10 to some power r, well, 3 times 10 to the 5th. This is a big number. This would be, well, if we write it out in standard form, we'd have 3 with 5 zeros, which is 300,000, a relatively large number. And we'll actually work on how to convert from one to the other and back and forth. Here, I have 5.324 times 10 to the negative third. Well, this value here is, even though it has a decimal within it, it is still between 1 and 10. 5.324 is still in between 1 or equal to, but less than 10. So we see that's how we would write a number in standard form. It may contain a decimal, but there can only be one non-zero digit in front of that decimal because it has to meet this requirement. If I were to write this in standard form, essentially what this tells me is this is a small number, a negative exponent, because we're dividing, right? That's our rules of exponents. So I'm going to move the decimal 3 spots to the left here. So I'd get, from here, 3 spots would bring it over here, a very small number. Notice the first non-zero digit is in the thousands. So it's a relatively small value. So how do we make these conversions? Well, for converting, there's 2 ways to go. If we have a number in standard form and we want to write it in scientific form, this is what we're going to do. If the number is greater than 1, maybe it's 2, or maybe it's a billion, some value greater than 1, we're going to move the decimal to the left, which will make our r, that power of 10, greater than 0, a positive number. So essentially, if it's a large number, or something greater than 1, we're going to have a positive power on our factor of 10. So if I want to write this number in scientific notation, it's currently in standard form, To write it in scientific notation, I have to have the decimal after the first non-zero digit. So I have to move it all the way over to here. Well, if I do that, I'm moving it 3, 6, 9 spots. So I'd have 9.3. And I don't have to worry about trailing zeros. But I move the decimal 9 spots, 10 to the 9th. Because I moved it to the left, this is a positive value. R is greater than 0. It's positive. So I have 9.3 times 10 to the 9th. Positive exponents means this is a large number. And we saw it came from that large number. What about small numbers? If our standard numbers are less than 1, well, this value, this is the ones place. Obviously, it's way less than 1, a very small number. To write it in scientific notation, we have to move the decimal to the right. To get it to that first non-zero digit, I have to put it right here. So I have to move it to the right. And when I do that, I get 1.85. But how many spots did I move it? 1, 2, 3, 4, 5 spots to get to here. Well, that's how many factors of 10? Well, it's 5 factors of 10. But it was to the right, making it a negative value, r less than 0. Anything less than 0 is negative. So small numbers have negative exponents when written in scientific notation. Large numbers have positive exponents when written in scientific notation. So we have to look at the value and just determine, is it greater than 1 or is it less than 1? Are we going to move it to the left or move our decimal to the right? All right, what if we're going the other way? What if we have numbers in scientific notation and we want to write them in standard form? Well, we do the opposite thing. In that example, we looked at r as the last thing to look at, positive or negative. Well, when we're going to write from scientific notation to standard, the first thing we look at is r. We're going to work it backwards. If r is greater than 0, that tells me that this is a number greater than 1. It's a large value. So to get it back into a standard form, I got to move the decimal the opposite way as I did here. Instead of going to the left for a large number, I'm going the other way. I got to go to the right. So I look at this and say, OK, 6 is my r value. It's positive. This is going to be a large number. I have to move the decimal 10 factors, or excuse me, the factor of 10 6 times. So move the decimal 6 times to the right. And when I do that, I move it 1, 2, 3, 4, 5, 6. I have to put in these zeros. Just like when I wrote this number, I eliminated the zeros. Well, now I have to put them back in. So we see this number is 9,056,000, a relatively large number, a positive r. What if we have an r that's less than 0? And I look at a number and say, hey, that's a negative r value. That tells me that that exponent makes this a very small number. So I have to move the decimal to the left, make this really small, further away from the ones spot. And if I do that, I just move it this many to the left. And if I do that, here's my 9, 0, 5, 6. Here's my digits. If I move the decimal 1, 2, 3, 4, and then I can put in my decimal. So we see that this 9 is 4 factors of 10 from the decimal, 4 factors of 10. And I like to put a leading 0 when I have decimals so that we don't miss that decimal symbol. So that's how we would convert from standard to scientific or scientific to standard. It's going to take some practice to get familiar with which way am I moving the decimal to go from one form to the other. So now if we look at some examples where we can apply rules of exponents, in the real world, we're going to deal with really big numbers, and we're going to deal with really small numbers. Scientific notation can help us simplify them, but we have to master those rules of exponents because they have exponents. Now, if I recall, if I had something like this, 2x times 4y. As an example, we'd just deal with the number first. 2 times 4 is 8. And then I would deal with these. X times y would be xy. We're going to do the same thing with this, but we're going to use our rules of exponents. If we look, I see, well, we have 2.5 and we have 2. I'm just going to multiply these numbers together. 2 times 2.5 is 5. Now I can deal with these exponents just like I did the x and y. Well, 10 to the 6th, 10 to the negative 6th. I can use the rule of exponent called the product rule because I'm multiplying them together, a product. So the product rule says I just add them. 6 plus a negative 6, well, that's the same as 6 minus 6, which would give me 10 to the 0. So 5 times 10 to the 0. Well, I can simplify that further because anything to the 0, one of my rules of exponents, the 0 rule, is 1. 5 times 1 is just 5. So even though I had this very large number, 2.5 million, times 2 millionths, very small number, we got a reasonable value of just 5. No reason to even have it in scientific notation anymore. Now, sometimes our numbers are in standard form. And to actually do this division, it might seem intimidating to have this really small number divided by a relatively large number. One thing we can do is convert it to scientific notation. Since this is a number less than 1, I know I'm going to have a negative exponent for r. So I have to move the decimal to the first non-zero digit. So I'd have 2.5. How many spots did I move it? 1, 2, 3, 4 times 10 to the 4th. But because it's a small number, I know my r is negative. And now, if I divide it by this, 5 with 4 zeros, well, that's 5 times 10 to the 4th. 4 zeros, right? So we moved the decimal 4 spots to get it right behind that first non-zero digit. And it's a large number, a positive exponent. So now I can look at this 2.5 over 5. Hey, well, that can reduce, because this is half of that. This would reduce to 1/2. So I'm just going to write it right here, 1/2. And then we have 10 to the negative 4th, 10 to the 4th. Well, I can use the quotient rule here. Negative 4 minus 4 would be negative 8 times 10 to the negative 8th. Well, we can't have this. This is not correct, because we can't have a fraction in scientific notation. So I'm going to convert this back to a decimal. And I could have done that if I did division here. I'd get 0.5. And hopefully we know that 1/2 is 0.5. If I had half a dollar, I'd have 50 cents, or 0.5, times 10 to the negative 8. Well, this is still not in proper scientific notation, because one of our rules of scientific notation is that the decimal has to be behind or to the right of the first non-zero digit. This one's 0, so it has to be in front of this one. I'm moving it to the right. So I'm taking a small number, less than 1, and I'm making it bigger. I'm moving it to the right. That means that this number is even smaller, so I got to make this even more negative. 5 times 10 to the negative 9th. I moved it to the right, so I'm going to add a negative 1 to that. So negative 9. 5 times 10 to the negative 9th. All right, so hopefully that kind of makes sense. And it'll come to you with practice, lots of practice. I want you to practice on this one here. Now, don't be intimidated by these values. It actually works out to be a nice number. OK? There is a decimal in it, but it's a nice number. So go ahead and try this one for yourself. Deal with these coefficients. Then deal with these factors of 10 using your rules of exponents. So this has been 7.1 with the appendix of scientific notation. Thank you for watching.